This week, learn how to use polyfit to fit things that aren't straight lines, such as exponential growth, decay, and power law fits. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. These days, we're hearing a lot about things like exponential growth and exponential decay, with fears of a virus that's circulating the globe. But we often see things like exponential growth and decay in science, as well as power law fits, which are where one variable is related to another through some sort of exponentiation, such as the square or the cube of that other variable. And these are actually pretty common in meteorology, especially when we're dealing with fields like turbulence and mixing. So I thought it would be a good idea to show you how to use polyfit, which we normally use to fit polynomials or lines, to evaluate fits to some of these more complicated functions. And really what it comes down to is you make it look like a line by doing a transformation. Instead of plotting x against y, you might plot x against log of y, or something similar, and then we fit a line to that. Now, if you're not familiar with polyfit, about a year ago, we did a MetPy Monday on basic fitting. There are a few caveats to doing this, such as if you're plotting on a log-log scale or a log-linear scale, that the weights are really uniform, and that's going to slightly bias the fit. Well, most of the programs that you've probably used to fit things like this in the past, such as Microsoft Excel, also just use even weights. Now, there is a way that you can specify weights to polyfit to give more weights to larger values, or use some other kind of weighting function, but we're not going to explore those. We're going to do what is matching some of these other programs. There's also a scipy.stats module that has some more sophisticated fits built in, but really I found a coordinate transformation in polyfit to be adequate for most all the fits I've done. Now, knowing that everybody is not an expert in turbulence or boundary layer or radiation or any other number of topics that we could come up with, I thought we would stick to geometry, though you'll see how this is very easily applied to any equation in your specific subset of the field. And I chose to do a power law fit or a log law fit. The word law in this always has driven me a little bit nuts because there's nothing physical law driven about it. It's just that this is the way it happens to fall out for many things. So let's go ahead and get started. Import NumPy and import matplotlib. And we'll use our matplotlib inline magic. So the problem that I've chosen to tackle is we want to determine how the side lengths of a square are related to the area of that square. Now, we know the answer here, and it's always good when you're trying to figure out if you really know how to use a function to tackle a simple problem that you know the answer to. I know that these areas should be related to the side lengths by the square of the side length. So we'll do this, we'll practice with our power law or log-log fitting, and we'll make sure we get the correct answer before you go on and do this on whatever fun meteorological application that you've got. So I'm going to create a variable called side lengths, and I'm going to make it in the range of 1 up to but not including 1,000 in steps of 100. Areas are going to be the side lengths times the side lengths. All right, so let's make a quick plot of that. And you'll notice I'm using the simple plot interface here. We're not going to create figures and axes, just for some quick dirty plots to look at. So side lengths and areas. And there we have our plot. We see it is not linear. We could absolutely fit a line to it, but that would extrapolate and interpolate pretty poorly, really. So how can we make this better? Well, let's try, as you often do when you're looking at data for the first time, some different plots. So I'm going to plot it on a semi-log x plot. So side lengths and areas. Okay, well that's interesting. It looks more like an exponential. Okay. Let's look at semi-log y. Yeah, still, okay, that's not going to be it either. Let's look at a log-log plot. And log-log plots, you can make a lot of jokes about them. The most common one is, well, anything is linear if you put it on a log-log plot and use a big enough line width, which there is a little bit of truth to that. But in everything from meteorology to geology and earthquake physics to almost any natural science field, you will find a lot of things follow this log-log or power law distribution. Okay, so I'm going to set the line style to be none. Remember that is the string none, not the type none. And the marker to be a circle to get rid of that line. So we can actually see the distribution of our data. As we see, this is poorly constrained here if you look at it in log-log space. So let's go ahead and fit a line. If you remember that polyfit returns the coefficients of fit. If we look at the documentation for it, it takes x, y, and the degree of fit. So what is our x? Well, fundamentally, it's going to be side lengths, and the y is going to be areas, and we want to fit it with a first degree polynomial. And before you start screaming at your screen, it's okay, we're going to come back and fix this. So there is our slope and intercept, and I see those are not necessarily things that look like any value I expect, but let's keep going. I'm going to find my fit y values using polyval. Polyval is going to take the coefficients that were returned by polyfit, and we'll evaluate them at whatever values we give. I'm just going to reuse my side lengths array and give us y values. So now let's plot that same plot. I'm going to copy and paste that line and add our fit. So we've already established this is going to be a log-log plot, though I could call log-log again here. I'm going to plot side lengths and fit y. Oh, that is not at all what we expected. Right. So the reason is we're plotting in log-log space, so we need to take the log of the x and the log of the y and fit that. Okay, well that's simple enough. I'm going to take log base 10 of side lengths, log base 10 of the areas, and let's rerun all those cells. Closer. It's at least a line now, but it is not a line that has anything to do with our data from what we can tell. So let's go back and look. Well, we're evaluating on log 10 of x, log 10 of y, but then we're evaluating that fit using just x. Well, we need to pass log 10 of the x as well. So let's go ahead and rerun these cells. And believe it or not, that actually made it a little worse. So where's the problem here? Well, what is being returned? Let's think about this. We're passing it log 10 of x, and it's fitting to whatever we put in the y here, which is log 10 of areas. But we're plotting just areas. It just happens to be that we're plotting them on a log plot. So how can we deal with this? Well, we need to take the base of our logarithm, in this case 10, and take it to the power of the fit value that is returned. We're undoing that log effectively. And once we do that, we see that we get a fit that goes right through our data. The procedure is exactly the same for any log linear fit. So instead of just putting log 10 on x and y, you would just put it on x or just put it on y. For an exponential growth or decay problem, you can take the log of both sides of the equation and get log 10 of y on one side and simplify that exponential on the right-hand side of the equation and perform the exact same fitting procedure. Again, there are some more advanced fitting procedures in SciPy.stats, but if you're trying to match your favorite statistical analysis program, this is most likely all that's happening under the hood. I hope that you found this useful, and I'll see you on next week's MetPy Monday.